Hi, this is Dr. Collins Jones. Welcome to segment 2 of my video series on measurement, significant figures, and basic data analysis. In this segment, we will cover powers of 10. This segment should be a quick review of scientific notation and how it is related to scientific prefixes. Let's start with a quick review of powers of 10. Very large or very small numbers are often expressed as powers of 10. This is our format, 10 to the power of b, where b is the power or the exponent of 10. As an example of how this may be applied, I've included here a little graphic that includes the size in meters of various items, objects, things that you may encounter in the physical world. So, if we're taking chemistry or biology, we think about atoms and molecules. The radius of a hydrogen nucleus is roughly 10 to the minus 15th meters. The size of a typical atom is 10 to the minus 10th meters, right? And then we look at things like the radius of the Earth, it's a little more than 10 to the 6th meters. But the point here is that all of these measurements are expressed as powers of 10. Okay, so before we continue, we just want to review the laws of exponents, that is the laws of powers. Okay, so remember that 10 to the power of 0, 10 to the 0, is equal to 1. 10 itself is the same thing as 10 to the first power, or 10 to the 1. And this comes in handy to remember when you're multiplying, say, 10 times 10 to the third, or 10 times 10 times 10 to the fifth, all right? There will be the law of multiplying powers of 10 together where we need to add things, and we see sometimes people forget to include that 10. 10 to the minus 1 is equal to 1 over 10 to the power of 1. So as I mentioned a minute ago, let's look at our exponent laws here. A to the power of negative m, right, and this is just algebraic symbols, is the same as 1 over a to the m. So if we look at that in terms of scientific notation and powers of 10, 10 raised to the power of negative 2 is the same as 1 over 10 squared, or 1 over 10 times 10, or 0.01. The product law says that if we multiply a to the m times a to the power of n, this is the same as a raised to the power of m plus n. So you look at something like 1,000, this is 10 times 10 times 10, or 10 to the first times 10 to the first times 10 to the first, which is 10 to the 1 plus 1 plus 1, or 10 to the third. Hopefully you're remembering all this from algebra. Okay, 0.001 is 1 over 10 times 1 over 10 times 1 over 10, or 10 to the negative 1 times 10 to the negative 1 times 10 to the negative 1, or 10 to the minus 1 plus minus 1 plus minus 1, or 10 to the negative third. And hopefully by now you're thinking, but my calculator does all this. Why do I need to worry about this? And you're absolutely right, but I think it's important that you recognize what's been programmed into the software or the firmware of your calculator. These arithmetic operations are what your calculator is doing for you. But if you kind of have it on the surface of your mind that this is what's going on, it helps when you review the answer displayed on the calculator screen to make sure that it actually makes sense. Okay. We also have the quotient law, where if we have a to the power of m divided by a to the power of n, this is a to the m minus n. And we have the power of a power law, a raised to the power of m, which is then raised to the power of n. This is a to the m times n. The last two we don't usually encounter in at least in our introductory chemistry classes or biology or biotechnology classes, but I thought I would include these just for completeness. So if we look at a few examples here, express the following as a power of 10. So 100,000. 100,000 is equal to 10 to the first times 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 10 to the first. 10 times itself 5 times, or 10 to the power of 5, positive 5. If we look at 0.0001, right, 0.0001 is 10 to the minus 1 times 10 to the minus 1 times 10 to the minus 1 times 10 to the minus 1, or 10 to the minus 4th. Okay, so just sort of to get you in the mindset of looking at scientific notation. Note, these are not measurements because there's no unit associated with these. These are just numbers, and we're expressing them as scientific notation. The general format for scientific notation is A times 10 to the power of B. But in some cases, we may use a slightly different variation of this. For example, A times 10 to the caret B, or A times EB, where E is exponent. The E there means exponent B, and that's taking the place of the number 10. Right? In this format, A is referred to as the mantissa, and A is a number between 1 and 10. So that is, A is greater than or equal to 1, but is less than 10. It can go up to 9.99999, but it's not 10. 10 is the base, and B is the exponent or power of 10. Right? B can be a positive or negative number. When we are dealing specifically with expressing numbers in scientific notation, B is a whole number. 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. Okay? If B is a positive number, B, 10 to the plus 2, then the numerical value is greater than 1, right? 10 to the plus 2 is 100. 100 is bigger than 1. If B is a negative number, then the value is less than 1. So 10 to the negative 2 is 0.01, and 0.01 is a smaller number than the number 1. Let's make sure that we can identify each part of this format. So if we have 2.34 times 10 to the 6th, right? 2.34 is our mantissa, that's our A. 10 is our base. And 6 is our power of 10, the B. Okay? In non-scientific notation, this would be 2,340,000, right? So it takes less space. It's easier to write out something in scientific notation than to write it out fully. In our second example, we have 7.05105 times 10 to the minus 4th. Okay. Again, our mantissa A is 7.05105. 10 is our base, and negative 4 is our power of 10, is our B. So one thing to really keep track of here is make sure, especially when you're giving an answer on an exam, or more importantly, you're documenting or recording data, that your signs, plus or minus in your scientific notation, are very clear and that they are there. And again, then this number expressed in non-scientific notation would be 0.000705105. Okay? Again, neither of these are measurements because there is no unit associated with them. Let's look at how to convert very large numbers or very small numbers into scientific notation. There are different ways to approach this. There are different ways to move the decimal point. So this is the way that I teach. You may have been taught a different way. If that's what you remember and that works for you, just skip this slide, move to the next one. Okay? All right. So what we want to do here is convert 8,325,000 to scientific notation. And note the decimal point here. Right? We haven't discussed significant figures, but we will in some upcoming segments. And so for right now, I'm going to encourage you to keep all of the zeros. If they are zeros at the end of the number, these are also called trailing zeros. So I'm just making the number bigger here so it's easier to see what I'm doing to make the conversions. So according to the format on the previous slide, we need to convert this number, 8,325,000, into a form of A times B to the A times 10 to the power of B. A times 10 to the power of B, where A is a number between 1 and 10, right? So this number is greater than 1, 8,325,000. So we know that our exponent B must be a positive number. So the first thing that we want to do is move the decimal point so that we get a number between 1 and 10, right? And so it looks like our number is going to be 8.32. So we just move the decimal point and we count each time we move the decimal point. So that's 1, we've moved it once, okay? And I put the little decimal point there, that little blue dot, just so you can see that we've actually moved it. We're going to move it again. This is the second time, right? Decimal point is there. We're going to move it again. Third time, move it again. Fourth time, okay? Because remember, our goal here is to get this number to between 1 and 10. Okay, move it again. Almost there. Okay, and then finally, the sixth time we've moved the decimal point, we now have the decimal point placed where our number is 8.325000, and this is a number between 1 and 10. Okay, so 8.325000 is a number between 1 and 10. We move the decimal point 6 places over, right? So we know the exponent is going to be positive. So this number expressed in scientific notation is 8.325000 times 10 to the positive 6. And again, we want to retain the zeros because later on when we talk about significant figures, these zeros may be important. Note, however, that your calculator may drop these zeros. It may just not include them in the display, and it's doing that to save memory space, but they're still there. The calculator just chose to ignore them. And of course, the other variations of how we could express this would be 8.32500 times 10 caret 6, or 8.32500 e to the 6. Okay. To go in the opposite direction then, let's look at converting 0.00008325 to scientific notation. And I have to admit, it's sometimes hard for me to keep track of reading all these zeros. So if I don't state the correct number of zeros verbally, please always refer to the number on the slide. Okay, so again, I'm just going to put this as a bigger number so we can easily see how we're moving the decimal. We want to keep in the format of a times 10 to the b, where a is our number between 1 and 10. And again, this is going to be 8.325, but our number 0.00008325 is less than 1, so the exponent has to be a negative number. So again, we're just going to move the decimal point till we get to the 8.325, a number between 1 and 10. And we're going to count the number of times we move it. So that's one place, right? There's our decimal, move it again. That's our second place, right? There's our decimal, move it again. That's our third place. Okay, move it again. That's our fourth place, all right? And move it again. That's our fifth place. Okay, and you know that when you first start to do this, you may actually draw these little arrows on your page as you solve the problem, right? Because until you do a lot of these, it doesn't become intuitive. So, take your time. Don't worry about what other people are saying. Do what you need to do to get the correct answer. And if that's drawing these little arrows, go for it, right? It's better to get a correct answer than to try to shortcut something. All right. So we've moved this 5 places. We now have 8.325, a number between 1 and 10. We count up 5 places to do this, so the exponent is going to be negative 5. So our number in scientific notation is 8.325000 times 10 to the 5th. But wait, hopefully you guys caught this mistake. There's no zeros after the 5 here, right? Right up here, there are no zeros here. So this is wrong, right? So just like you can't drop zeros, right? You also can't just add zeros. So really, this number is going to be 8.325 times 10 to the minus 5th. Or expressing the different variations of this, 8.325 times 10 caret minus 5, or 8.325 e to the minus 5th. Okay? All right, so here are a few practice problems to try convert each of the following numbers, again, not measurements because there's no unit there, into scientific notation. So I really encourage you to just try this. Pause this presentation for a minute. I'm going to count to 3, and then when I come back, I will fill in the correct answers in the table. So give it a shot. First one, 2.104 times 10 to the positive 2. 5.4018900. We kept the zeros. Remember, your calculator maybe didn't do that if you tried to solve this on a calculator. Times 10 to the plus 5. 8.047 times 10 to the negative 3. This is a long one. I'm just going to display it. All right, but it's times 10 to the 9th, plus 9th. And I really like to put the plus sign in there. Some people don't, but I like to make it clear that it's either positive or negative. So I'd like to include the plus signs in my answers. Here we have 5.287 times 10 to the minus 2. Another long one, times 10 to the minus 7. And then look, this one it's already a number between 1 and 10. So technically, this is considered to be already in scientific notation. We don't need to do anything to it. All right. So hopefully you did pretty good on these. There's actually a site that also covers a slightly different way to convert a number into scientific notation. And you can put a number into this website and it will automatically, once you enter the number and press return, press enter, it will convert that number into scientific notation for you. So I thought I would just include that site. Okay, prefixes. Prefixes are often used to represent scientific notation. A prefix is a letter symbol that represents a specific power of 10. We developed these in the days before we had word processing because, as you guys don't remember this, but I remember typewriters where if you wanted to make something a superscript or a subscript, the typewriter actually had this little roller and you manually had to turn the roller up or down to do a subscript or superscript. And that was really challenging to get everything aligned properly. So people just came up with these letters and said, okay, right, here's a letter. We have kilo, right, 10 to the plus 3. So whenever I put a K in front of a unit, it just means it's times 10 to the plus 3. Milli is 10 to the minus 3. Micro is 10 to the minus 6. Nano is 10 to the minus 9th. Pico is 10 to the minus 12th. And femto is 10 to the minus 15th. And you may have noticed that these SI units are expressed as multiples of 10 to the power of 3. This is also an engineering notation. So what I've put here are the most commonly used prefixes in chemistry, biology, biotechnology, the pharmaceutical industry. So you should memorize these prefixes, right? You should memorize these prefixes. You should know the name, you should know the symbol, and you should know what power of 10 they represent. And you should also keep the case, upper or lower case, in mind here. And in this case, all of these are lowercase. Notice that micro is the Greek letter mu. It's a U with a little tail on it. But sometimes people just write U because they're lazy or they can't find the symbol conversion on their PC. Okay, but these are prefixes, right, that you should commit this table to memory and be comfortable using it. So how do we get comfortable using this? All right. Express the following without the prefix. So 35.1 milligrams. So we have milli, and I know that you've already committed this to memory. So really what we have here is 35.1 times 10 to the minus 3. The times 10 to the minus 3 just substituted in for the milli. And so when we do the math for this, okay, what happened here? When we do the math for this, it's 0.0351 grams. Kilograms, 0.07642 kilograms. So really, I like to do these very straightforward. Just say K is times 10 to the plus 3. So just substitute that in. And now you can put this into your calculator and let it do the math for you. And it's 76.42 grams. Okay. Try the next one. 175.0 microliters. So just set it up. How would you do that? And it would be 175 times 10 to the minus 6, because micro is times 10 to the minus 6. When you do the math, it's 0.000175 liters, right? 22 nanoseconds, that's a really short amount of time, right? 22 nanoseconds. This is 22 times 10 to the minus 9th seconds. Or we might even keep this one because it's so small in scientific notation. And so this would be 2.2 times 10 to the first. 22 is 2.2 times 10 to the first times 10 to the 9th. Or 2.2 times 10 to the power of 1 plus minus 9, which is 2.2 times 10 to the minus 8th. And again, your calculator will do this for you, but I just want to go through how it accomplishes that. 35.9 kilograms. Go ahead, fill it in. Right? 35.9 times 10 to the positive 3, or 3.4 times 10 to the plus 4th grams, right? Or 3,400 grams. And then 545.2 milliliters. This would be 545.2 times 10 to the minus 3 liters. Just put in the times 10 to the minus 3. We get 0.5452 liters. And it is important, and we stress this in our documentation lectures, it is important that you put the 0 there. Don't just put the decimal point, put 0.5452. The 0 is important because sometimes the decimal point is lost, and that can cause huge errors. All right. All right. In the next table, we're doing the reverse. I made this work out very nicely. It doesn't always work out this nicely, but I didn't want to spend a lot of time in this segment. It's already taking a long time, but just sort of illustrate how we might do this. So we have 2,583 grams. And if we convert that into scientific notation, that's 2.583 times 10 to the plus 3 grams. And so look, times 10 to the plus 3 is kilograms. So we just replace the times 10 to the plus 3 with the letter K for kilo, lowercase. 0.00162 liters. This is 1.62 times 10 to the minus 3 liters. Guess what? Times 10 to the minus 3 is milli. So we replace the times 10 to the minus 3 with milliliters. All right, I'm not going to read this one all the way out because I know that I'm going to omit or add an extra 0. So this is going to be 3.84 times 10 to the minus 6 grams, right? And you should have been able to figure that out, all right? And times 10 to the minus 6 is what? Micro. So this is 38.4 micrograms. And notice we have the Greek letter mu here with a little tail on the U. And then the last one, 0.00427 grams. This is 4.27 times 10 to the minus 3 grams, or 4.27 milligrams. And so again, I made these work out really nice, okay, for the purposes of our illustration, okay, but they don't always work out this nice, and we'll cover that a little bit later. Do you guys see, I just noticed, do you guys see any mistakes here? Okay. I did, all right, because I changed this up when I was actually making this slide. So 38.4 should really be 3.84, right? This really should be 3.84. The decimal is in the wrong place, all right? So it's always important to double check your work, which I apparently didn't do here. So sorry about that. But this should be 3.84 micrograms. And this is why, for example, pharmaceutical and biotech companies have a unit called the Quality Assurance Unit, the QAU, and their job is to look for and point out mistakes like this before the data goes to the FDA, before the drug is released to the patients. Okay. This table is just all of the currently known or assigned prefixes. This is in 2024. So you don't have to memorize all this, but I just thought it was pretty cool because they keep increasing the magnitude of the powers of 10, and most of this has to do with increased computing power. Okay, finally, how to enter scientific notation and prefixes on your calculator. And I've included this because when I used to teach chemistry, lots of times students, their answers were off by a factor of 10. It was either 10 times too big or 10 times too small. So if I want to enter something like 25 kilograms, right? Here's what we're thinking. 25 kilos is 25 times 10 to the plus 3, since kilo is 10 to the plus 3. So to enter, this is the key, to enter the times 10 to the plus 3, your calculator should have an EXP or an EE key. If it has a 10 to the X key, do not use that. Look for the EXP key or the EE key, all right? That key, when you press EXP or when you press EE, that is really times 10, all right? So, and you should see a little number 00 appear on the right-hand side of the screen, okay? So it won't, some say times 10, but most don't say times 10. It just assumes it's times 10 to whatever power you're going to enter. So the way you would do this is you would key in 25, then you would press the EXP or the EE key, and then enter in the exponent only, in this case plus 3, okay? Because again, the EXP is times 10. So the keystroke sequence would be enter in 25, press EE or EXP, okay? Or whatever else you may have to read the directions, whatever else it's going to use to be times 10 to whatever. Then you press the plus key on the plus minus, right? Don't plus the add or subtract key. You have to hit the plus minus. And you press 3, and now your display should look 25 to the power of 3. And the 10 is omitted, but because it's a superscript, it's there, or because this power of 10 is separated on the right-hand side of the keyboard from the other numbers, you know that it's whatever exponential power that is. Okay? And so that might be the screen display. If it really does scientific notation correctly, when you press equal again or go to do something, it will say, well, this is 25, which is really 2.5 times 10 to the 1. And since it's 2.5 times 10 to the 1 times 10 to the third, that's 2.5 times 10 to the 1 plus 3, or 2.5 times 10 to the fourth. That's what's going on in your calculator. And that is the end of our review. But let's do one more. Sorry, one more. Try this one, okay? To enter 175 microliters, go 175 EE. We know that micro is minus 6, right? So we're going to have 175 times 10 to the minus 6, but your calculator will do the correction. So this will be 175 is 1.75 times 10 to the power of 2. So 1.75 times 10 to the power of 2 times 10 to the minus 6 is 1.75 times 10 to the 2 plus negative 6, which gives us 1.75 times 10 to the minus 4th. And that, after we see the screen display, that is the end of segment 2.